The question, are we alone? It is, in a sense, the oldest question, or at least one of them. Human beings have looked up at the night sky for as long as there have been human beings, and at some point in that long and patient looking, the question must have arisen. Those lights up there, are any of them inhabited? Is there anyone else, anywhere in all of that, who is looking back? For most of human history, the question was purely philosophical, unanswerable by any means available to us, a matter for speculation and for wonder and for the various frameworks, religious and mythological and philosophical, through which different cultures have tried to locate themselves in relation to the rest of existence. Some traditions assumed a universe full of beings. Others assumed human beings were unique. The question could be asked, but it could not be investigated. There were no tools adequate to the task. What is extraordinary about the moment we are living in is that it may be the first time in the entire history of our species that the question is not merely askable but answerable. Not yet answered, but answerable. We have built the instruments. We have developed the science. We are, for the first time in human history, actively and systematically searching for life beyond Earth, with tools powerful enough that a positive result is genuinely possible. And within the lifetimes of many people alive today, we may have an answer. Possibly within decades, possibly sooner. Tonight we are going to explore that search, what we are looking for, where we are looking, both nearby and across interstellar distances, what we have found so far and what it suggests, what the different possible answers would mean for our understanding of life and of the universe and of ourselves. Because the answer to this question, whichever way it falls, will be one of the most significant discoveries in the history of human knowledge. Either answer will change everything. So let yourself settle, let your breathing slow, and let the full immensity of the question settle around you gently. The scale of the possibility. To understand why serious scientists take the search for extraterrestrial life seriously, you need to spend a moment with the scale of the universe. The observable universe, the portion of the universe that light has had time to reach us from since the Big Bang, contains an estimated 2 trillion galaxies. 2 trillion, 2 followed by 12 zeros. Each of those galaxies contains, on average, somewhere between 100 billion and 1 trillion stars. Our own galaxy, the Milky Way, is a fairly average galaxy. It contains somewhere between 100 and 400 billion stars. We now know, from data gathered by the Kepler Space Telescope and the missions that followed it, that the majority of those stars have planets. The earlier assumption, which persisted into the late 20th century, that planets might be relatively rare, something special about our solar system rather than a standard outcome of star formation, has been definitively overturned. Planets, it turns out, are everywhere. Some estimates suggest there may be more planets in the Milky Way than there are stars. Within the Milky Way alone, the number of planets orbiting their stars at distances where liquid water could exist on their surfaces, the so-called habitable zone, is estimated at somewhere between tens of billions and hundreds of billions. Tens of billions of potentially habitable planets. In one galaxy, out of 2 trillion, the physicist Enrico Fermi, confronted with numbers something like these during a lunchtime conversation at Los Alamos in 1950, posed what became known as the Fermi Paradox. If the universe is so vast, he asked, and if habitable planets are so common, and if the universe has been around for 13.5 billion years, long enough for intelligence to have arisen and developed spacefaring capability many times over, then why, asked Fermi, is there no evidence of any of it? Where is everybody? The silence of the universe, in the face of the enormous statistical expectation that it should not be silent, is one of the deepest and most unresolved puzzles in all of science. We will return to it, but first let us look at what life actually needs and where in our neighborhood the conditions for it might exist. What life needs. To search for life, you need a working definition of what you are searching for. And this turns out to be harder than it sounds, for reasons that are more interesting than merely definitional. Life on Earth is extraordinarily varied. From the bacteria that thrive in boiling hydrothermal vents to the organisms frozen into Antarctic ice to the creatures living in the crushing darkness of the deep ocean floor, the range of environments in which life has found a way to operate is far wider than biologists of a century ago would have predicted. The lesson of this diversity is that life is more adaptable, more resourceful, more capable of exploiting extreme environments than we initially assumed. The working consensus in astrobiology, the science of life in the universe, is that life as we know it requires three things: a liquid solvent in which chemistry can take place, a source of energy, and a supply of the complex organic molecules that biological structures are built from. Water is the best candidate for the solvent, for reasons that go deeper than familiarity. Water has a remarkable set of chemical properties that make it exceptionally well suited to hosting the kinds of complex chemistry that life requires. It is a powerful polar solvent, able to dissolve a vast range of substances and mediate an enormous variety of chemical reactions. It remains liquid across a wide temperature range. It is abundant throughout the cosmos because hydrogen is the most common element in the universe and oxygen is the third most common, and water is simply two hydrogens and an oxygen. Carbon forms the backbone of all known biochemistry because of its unique ability to form long, complex, stable chains and rings of molecules. The chemistry of life requires molecules of extraordinary complexity, molecules containing hundreds or thousands of atoms arranged in precise three-dimensional structures. Carbon, with its 4 bonding sites and its ability to link to itself and to a wide variety of other atoms in stable configurations, is the only element known to support chemistry of this complexity under the conditions prevalent on habitable planets. Could life exist based on different chemistry? Silicon shares some of carbon's bonding properties and has been proposed as an alternative backbone for life in environments hostile to carbon chemistry. Liquid methane or ammonia have been proposed as alternative solvents in very cold environments. These are genuine scientific possibilities, not merely science fiction. But we have no examples of such life to study, which makes it impossible to assess their likelihood. When we search for life, we search, of necessity, for the kind of life we know. The search close to home. The nearest candidates for life beyond Earth are not among the stars. They are right here in our own solar system, orbiting the same sun as we do. Mars is the most discussed candidate, and for good reason. The evidence that Mars was once warm and wet, that liquid water flowed on its surface for millions of years, that the conditions for life as we know it existed there in the ancient past, is now well established. Whether anything arose in those conditions, and whether anything survives today in the deep subsurface where liquid water may still exist, are open questions that the current Mars missions are specifically designed to address. But Mars, for all its interest, may not be the best candidate in our neighborhood. Europa. Europa is one of the 4 large moons of Jupiter, first observed by Galileo in 1610. From a distance, it looks like a billiard ball, its surface almost perfectly smooth and very bright, crisscrossed by long dark lines that are visible even through a moderate telescope. Those lines, which turned out on closer inspection to be cracks in a surface of water ice, were the first indication of what lies beneath, because ice cracks when it is stressed. And ice floating on a liquid ocean is stressed by the tidal forces of the body it orbits, flexing as it moves through the varying gravitational field. The cracks in Europa's surface are evidence of a global ocean of liquid water beneath the ice. The evidence has been confirmed and strengthened by multiple subsequent missions. The magnetic measurements made by the Galileo spacecraft detected a conducting fluid beneath the surface, most consistent with salt water. The surface geology shows regions where the ice has broken up and refrozen in new configurations, exactly as surface ice does when the liquid beneath it moves. And the Hubble Space Telescope has detected plumes of water vapor being ejected from the surface in some locations, suggesting that the ocean below is active and in some places in direct contact with the surface through cracks. This ocean is estimated to be twice the volume of all of Earth's oceans combined. It has been in contact with a rocky seafloor for perhaps 4 billion years. The tidal flexing of Europa by Jupiter's gravity generates heat in the interior, enough to keep the ocean liquid. And where there is a rocky seafloor, liquid water, and a source of heat, there may be hydrothermal vents. And where there are hydrothermal vents on Earth, there is life. NASA's Europa Clipper mission, launched in October 2024, is currently traveling to Jupiter. It will arrive in 2030 and then conduct dozens of close flybys of Europa, studying the ice, the ocean, the magnetic field, and the plumes, looking for biosignatures and building the case, or perhaps the absence of a case, for life in the ocean below. Enceladus. If Europa is the most promising candidate in the outer solar system, Enceladus may be the most immediately exciting. Enceladus is a small moon of Saturn, only about 500 kilometers across. By any prior calculation, it should be a frozen, dead, geologically inert world, too small to retain internal heat, too far from the sun to have liquid water on its surface. It is not. In 2005, the Cassini spacecraft, passing close to the south pole of Enceladus, detected something extraordinary. Enormous plumes of water vapor and ice particles erupting from long fractures in the ice near the South Pole, the so-called tiger stripes, and being ejected hundreds of kilometers into space. Some of the ejected material escaped Enceladus's gravity entirely and went on to form Saturn's E-ring. Enceladus was actively venting its interior into space. Analysis of the plume material by Cassini's instruments revealed a chemical inventory that made astrobiologists sit up sharply. Water, organic molecules of multiple kinds, including some of the building blocks of amino acids. Molecular hydrogen, which can be produced by the reaction of hot water with rocks in a process called serpentinization, and which is an energy source for certain kinds of microbes on Earth. Silica nanoparticles that can only form at temperatures above 90 degrees Celsius in contact with liquid water, indicating hydrothermal activity. And in results announced in 2023 from a reanalysis of the Cassini data, phosphorus. Phosphorus is one of the 6 elements considered essential for life as we know it. Its detection in the plumes of Enceladus, emerging from a liquid water ocean in contact with a rocky seafloor with active hydrothermal systems, was described by one of the researchers involved as the most complete set of abiotic requirements for life ever found outside Earth. And the extraordinary thing about Enceladus is that we do not need to land on it and drill through the ice to sample its ocean. The ocean is ejecting itself into space. A future spacecraft designed to fly through the plumes and analyze their contents in detail could potentially detect biosignatures, evidence of life, without ever touching the surface. Looking to the stars. Beyond our solar system, the search for life has been transformed over the last 30 years by the discovery and characterization of exoplanets. For most of human history, the existence of planets orbiting other stars was assumed by some philosophers and denied by others but confirmed by nobody, because no instrument existed that could detect them. The first confirmed detections came in the early 1990s. By the time the Kepler Space Telescope concluded its primary mission in 2018, having stared at a single patch of sky for 4 years and monitored the brightness of over 150,000 stars, it had identified over 2,500 confirmed exoplanets and thousands of additional candidates. Subsequent missions have continued the inventory. Among the most significant discoveries for the search for life is the TRAPPIST-1 system, a small, cool, red dwarf star located about 40 light-years from Earth, discovered to have 7 rocky planets in 2017. 3 of those 7 planets orbit in the habitable zone, the range of distances from the star where liquid water could exist on a planetary surface. 3 potentially habitable worlds, all smaller than Earth but of similar composition, orbiting a single nearby star. 40 light-years is an unimaginable distance in terms of any travel we could currently contemplate. But it is close enough for the James Webb Space Telescope to study the atmospheres of the TRAPPIST-1 planets in some detail. And the atmospheres of exoplanets are where the most promising search for biosignatures, chemical signatures of life, is currently focused. The presence of oxygen in significant quantities in a planetary atmosphere would be strong evidence for life, because oxygen is chemically reactive and would rapidly combine with other substances and disappear from the atmosphere without a continuous biological source replenishing it. The simultaneous presence of both methane and oxygen would be even more compelling, because the 2 gases react with each other and cannot coexist in equilibrium without something continuously producing both of them. On Earth, that something is life. The James Webb Space Telescope is, right now, observing the atmospheres of exoplanets. The data it gathers over the next decade may be the first to show us a biosignature, the first chemical fingerprint of life on a world orbiting another star. If it does, the news will be among the most significant ever reported. SETI and the silence. The search for microbial life and the search for intelligent life are very different endeavors with different methodologies and different implications. The search for extraterrestrial intelligence, SETI, has been operating in various forms since Frank Drake pointed a radio telescope at 2 nearby stars in 1960 and listened for signals. The reasoning behind SETI is straightforward. A technologically advanced civilization would produce electromagnetic radiation, either intentionally as a beacon or unintentionally as the leakage from its communications technology. Radio waves and other forms of electromagnetic radiation travel at the speed of light and can cross interstellar distances. A sufficiently sensitive receiver should be able to detect them. After more than 60 years of searching, with progressively more sensitive instruments covering progressively more of the sky and more of the electromagnetic spectrum, the result has been silence, or very nearly silence. In 1977, an astronomer named Jerry Emin, working at the Big Ear Radio Telescope in Ohio, detected a signal so anomalous that he circled it on the printout and wrote the word "wow" in the margin. The signal lasted 72 seconds, the maximum duration observable with the telescope's design, and had the characteristics that SETI researchers had predicted a genuine extraterrestrial signal might have. It was never detected again, despite numerous attempts, and it has never been explained. The WOW signal remains the most tantalizing single data point in 60 years of listening. The silence is itself a significant fact. It does not prove that no intelligent civilizations exist. Our search has covered a tiny fraction of the possible search space, examining a small portion of the sky in a limited range of frequencies for what is, in cosmic terms, an eye blink of time. Absence of evidence from an incomplete search is not evidence of absence, but it is information. The silence constrains the possibilities, even if it does not resolve them. The Fermi Paradox revisited. The Fermi Paradox, the apparent contradiction between the enormous statistical expectation of other intelligent civilizations and our complete failure to detect any evidence of them, has generated a large and varied collection of proposed solutions. Perhaps intelligent life is extraordinarily rare. Perhaps the sequence of steps required to produce a technological civilization capable of interstellar communication, from chemistry to cells to complex organisms to language to technology, is so improbable at each step that, despite the vast number of opportunities, it has happened only once in the observable universe, or a very small number of times. We may simply be first or nearly first. Perhaps civilizations reliably destroy themselves before they become detectable. Perhaps the development of increasingly powerful technology outpaces the development of the wisdom to use it safely, and civilizations reliably reach a threshold of destructive capability before they reach the capability for interstellar communication. This is called the Great Filter Hypothesis, and if the filter lies ahead of us rather than behind us, it is the most sobering possible interpretation of the Fermi Paradox. Perhaps we are looking in the wrong way. Perhaps civilizations that survive their technological adolescence transition to forms of communication that we have not thought to look for, using physics we do not yet know or technologies of a kind we cannot currently imagine. Perhaps radio is a brief phase in the development of communication technology, used only by young civilizations, and the universe is full of conversations in modes we have not yet discovered. Perhaps interstellar travel and communication are simply too expensive and too slow for any civilization to bother with, and the universe is full of isolated civilizations that have looked at the distances involved and concluded, quite rationally, that there is nothing out there worth the effort. Each of these resolutions implies a very different universe and a very different future for our own civilization, and none of them can currently be ruled out. What the answer would mean, suppose we find it, suppose within the next decade or two, the James Webb Telescope detects an unmistakable biosignature in the atmosphere of a TRAPPIST-1 planet, or a Europa Clipper successor finds organic molecules and the chemical signatures of metabolism in a sample of European ocean water, or a reanalysis of the Perseverance rock samples returned from Mars finds structures that can only be explained by biology. What would it mean? At the most immediate level, it would mean that life is not a singular accident, that the chemistry of life, given the right conditions, arises not once in the universe but multiple times. And if it arises in two places in our own neighborhood, the implication, by any reasonable statistical inference, is that it arises everywhere the conditions are right. Life would be a common feature of the universe, something that the cosmos does routinely wherever it has the opportunity. The philosophical and theological implications would be profound in ways that are difficult to fully anticipate. Every tradition that has placed human beings or life on Earth at the center of a universe created for their benefit, would need to reckon with the revelation that the universe is full of life, that we are one instance among very many, that the cosmos is not our story but something vastly larger and more various than any story we have told about it. And now consider the other answer. Suppose we look carefully and thoroughly with the best instruments we can build, and we find nothing. Not in our solar system, not in the atmospheres of nearby exoplanets, not in any direction at any frequency, for as long as we are able to search. That answer would be, in a different way, equally momentous. It would suggest that we are something extraordinary, not the expected product of universal processes, but something rare and perhaps unique. It would not diminish us. It would, in a certain sense, make us more significant than we tend to feel in the face of the universe's immensity. The silence around us would not be evidence of our smallness. It would be evidence of our singularity. Either answer changes what we are. Either answer changes the universe we live in. Look up, in your mind's eye, at the night sky. All those points of light. Every star you can see is a sun. Most of them have planets. Some of those planets are at the right distance for liquid water. Some of them, right now, may be home to something. We do not know if they are. That is the honest and the complete answer. We are at the very beginning of this search, equipped with instruments only recently powerful enough to begin asking the question properly. The universe has been available to search for 60 years. We have been searching for 60 years with one civilization on one planet in one small corner of one medium-sized galaxy out of 2 trillion. Whatever we find, and whenever we find it, the search itself is one of the most extraordinary endeavors our species has ever undertaken. A question that asks not only what is out there, but what we are, whether we are alone or accompanied, whether the universe is aware of itself in one place or in many. Let that question sit with you gently tonight, not as something demanding an answer, not as something to be anxious about, simply as what it is, the largest question there is, held with wonder rather than urgency. The universe is vast beyond imagining, old beyond comprehension, full of things we have not yet found. Let your breathing slow. You are safe. You are resting. And somewhere out there, in the vast and ancient dark, the question hangs unanswered, as it has always hung. Good night.